So in this video, I'll do two more examples of applications of conservation of energy involving friction. So please tap the like button and subscribe. Thank you. So if there are external forces that do work, then the work done by the applied external force equals the change in the mechanical energy, which is delta K, which is change in kinetic energy, plus delta U, which is change in potential energy. If friction is involved, we just add a term for the increase in thermal energy because of the work done by friction. So we have delta K plus delta U plus delta E thermal equals 0. And then if there's an applied external force doing work on our system, then that applied external force will equal the change in kinetic plus change in potential plus delta E thermal. Where again, the increase in thermal energy, the delta E thermal, is equal to the positive value of the work done by friction. Remember, friction does negative work on our system, which means that we'll have an increase in thermal energy equal to the positive value of the work done by friction. All right, here's another example. We have a block of mass little m is released from rest at a height h on a frictionless ramp. At the end of the ramp is a spring with a force constant k. And just in front of the spring is a rough spot of width d. So this could be a toy and we spilled our apple juice on the track, so it got a little sticky in that spot. Alright, so we have a rough spot of width d. The coefficient of kinetic friction between the rough spot and the block is given as mu sub k. So part A, when the block is released, it slides down the ramp over the rough spot, then it compresses the spring, stopping momentarily. Find the maximum distance x the spring is compressed. Alright, so think carefully about what's going on here and how are we going to solve this. Now we have a little bit of friction involved. Again, we're just applying conservation of energy principles. And remember, we only have to think about how it starts and how it finishes, and then add the extra term for the friction. So our conservation of energy, we have the change in the potential plus the change in the spring potential plus the delta E thermal equals 0. Notice there's no kinetic energy term. Why is that? Well, we're going to start from rest, and at the end it's going to compress the spring and stop momentarily. So our initial kinetic energy is 0. Our final kinetic energy is 0. So we don't need to worry about how much kinetic energy it has in between. And the delta E thermal is just the frictional force times the distance, the friction x. So we don't need any kinetic energy for that either. So we're going to lose gravitational potential energy. The spring potential energy is going to increase and the thermal energy will increase. Alright, so our gravitational potential energy is going to decrease. We're going to lose height h, so that term is minus mgh. The spring potential energy is going to increase by 1/2 kx squared, where x is the distance the spring is compressed. And that's what we want to find. The increase in thermal energy is just the frictional force times the distance. And we're given the coefficient of kinetic friction. And we can realize that when it goes over the rough spot, the only vertical forces are the normal force up and the weight down. So the normal force will equal to mg. So we solve for x, so I have 1/2 kx squared equals mgh minus mu mgd, and then x equals the square root of 2mg times the quantity h minus mu d, and then all that over k. Okay, so we've got the answer. So given the mass, the height, the coefficient of friction, the distance, and the spring constant, we've got the value for x. Alright, part B. After compressing the spring then pushes the block back along the track over the rough spot and then back up the hill where it comes to a stop. What is the final height the block reaches? Okay, so how are we going to do this one? So think about it. All right, so the easiest way to do this part of the problem is just start from the very beginning. Notice that at the very beginning, we start with the block at a height h. So it's all gravitational potential energy. That's the total energy that we have in the system. So it's going to slide down, go over the rough spot, compress the spring, and then the spring will launch it back over the rough spot and back up the hill where it comes to rest. And its final energy will just be its final gravitational potential energy plus the thermal energy caused by 2 trips over the rough spot. We don't have to consider the spring at all because all the spring does is absorb some kinetic energy and then put it right back in the system. So the only changes in energy are the change in the gravitational potential energy and the increase in thermal energy because of 2 trips over the rough spot. We don't have to consider any kinetic energy or any spring potential energy. Thus, over the whole trip, the only changes in energy is there's going to be a change in the gravitational potential energy and a change in thermal energy. So the loss of the gravitational potential energy plus the increase in thermal energy must sum to 0. So the change in potential energy, we have mgh final minus mgh initial plus the increase in thermal energy, which is the frictional force, times the total distance, which is 2d. So we go 2 trips over the friction to give us the increase in thermal energy. So then we get mgh final minus mgh plus the frictional force now is just the coefficient of kinetic friction times the normal force. And in this case, the normal force is just equal to the weight mg and then times the 2d, and that sums to 0. So we have an mg in each term, so that divides out, and we get h final minus h plus mu times 2d equals 0. Solving for h final, we get our initial height minus 2 mu times the distance over the friction. And so we've got the answer. And look how simple this is. We don't have to consider any kinetic energy changes or any spring potential energy changes. All right, here's one more problem involving friction. We have a mass m is released from a height of 0.8 meters from the left-hand side of the track shown in the diagram. There's only friction acting along the horizontal portion, which is 0.3 meters on either side of the midpoint, 0. There's a coefficient of kinetic friction over this flat spot of mu sub k equal to 0.4. So we want to determine part A, how many times does the mass m pass through the midpoint, and part B, how far from the midpoint does it come to rest? All right, so think about how you would solve this problem. So go ahead and pause the video and try to solve this problem yourself and see if you can come up with the answer before moving on and seeing what the final answer is. All right, so we don't even have to think about kinetic energy here. Our initial energy is gravitational potential energy, the mgh. Our final energy then is going to be all thermal energy. We're going to convert all of our gravitational potential energy into thermal energy. And we can find the thermal energy by just taking the frictional force times the total distance that it passes through the portion that has the friction. So we just set our initial potential energy, mgh, equal to our final thermal energy, which is the frictional force times the total distance. Then, once we have the total distance, we compare that to the length of the rough portion, and the rough portion then has a total length of 0.6 meters. And then we can figure out how many times it went across and where it ends up. All right, so here's the equation. We have our initial potential energy, mgh, will equal our final thermal energy, which is the frictional force times the distance. Well, when the block is over the horizontal rough spot, the normal force is just equal to the weight, mg. So the frictional force then is just mu sub k times the normal force, mg, and then the total thermal energy then is that frictional force times the distance. So we have mgh equals mu sub k times mg times d. Notice we have the same mg on both sides, so that divides out. And so we get the height h equals mu sub k times d, and then d equals h over mu sub k. Well, the height h was 0.8 meters, mu sub k was 0.4, and so that gives us a total distance of 2 meters. So it slid a total distance of 2 meters over the rough spot. Well, the rough part is 0.6 meters long. It's 0.3 meters on each side of the midpoint, so a total distance of 0.6 meters. So if we make 3 trips across, that gives us a total distance of 1.8 meters, and so we have an additional 0.2 meters left. So it will go across 3 times, and after 3 crossings, it will be on the right side, and then it will travel in addition to the left an additional 0.2 meters, stopping at 0.1 meters to the right of the midpoint. Okay, so that's the end of this video, and that's the end of the examples that I will do for conservation of energy. So the next video I make, we will move on into the next section where we'll talk about systems of particles, center of mass, and momentum. So don't forget to like this video and please subscribe. If you have any questions, comments, or suggestions, please leave those as well, and I'll do my very best to answer all of your questions. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.